Can you hear me in the back? Can you see me? Okay. I haven't actually taught in this lecture theater for a few years now, and I had to go around twice to find it. But finally I'm here. So I'm sure Dr. Jenkili has told you that I'll be taking over from this week on. Or at least he told you in the first lecture. Maybe you don't remember, but here I am. My name is Hani Abdulatif, and I'm a lecturer in the economics department. And I'm very pleased to take over half of this module from now to the end of the semester. I'll try to do, I'll just give some introduction to what I'm planning to do in this lecture and what topics I'm planning to cover in the next few lectures. But before I do that, here's my my office hours. So Mondays, Tuesdays, 10:30 to 11:30, and my office is in the School of Management building, room number 208. Feel free to come anytime to my office hours, and I follow an open door policy. So it means if you're passing by chance, if passing by my office outside the office hours and you saw me there, just and you have any question, just come in. So it's not a big deal. Okay? So please feel free to come and see me anytime. Just importance. The reason we have office hours that you are 100% sure that I am there, and if I'm not in the office during the office hours, I'll probably email everyone saying I can't make it today for whatever reason. But generally, I should be there during the office hours. But as I said, outside the office hours, if you want to see me, or if you're passing by chance and you saw me there in the office and you want to talk about something, just come and talk about it. So that shouldn't be a problem. And also, you could email me if you still want to arrange or have a different arrangement. So that's fine. And guess what? You can also find me online. So you see, you find me everywhere. So you can find me in Twitter, Facebook. I have my own Hanomics webpage. I post usually lecture materials, recording. I have my Hanomics YouTube channel. This lecture will be in Hanomics on YouTube channel. So I'm not using lecture capture. I've been using my own YouTube channel for years now. So you'll see other lectures there. Maybe you can also see the lectures from the next year module, International Economic Policy, which I teach. It's an optional module. I'm not trying to advertise my module, but I'm saying there are lectures there. So you can see if you would like to attend this take this module. Anyway, so as I said, Hanomics is the YouTube channel where I'm recording. This recording hopefully will be there. Feel free to follow Hanomics. I have more than 198 subscribers. That was the first year I started Hanomics. So what I'm going to cover, there are a few topics I'm planning to cover in this in the rest of this module. Today I'll be talking about functional forms, and I'll explain what that means. And I'll give a very brief introduction to what you have covered. I'm not going to explain everything, but I'm just going to give an introduction that will lead to what I'm planning to talk about today. So we'll link both topics together. So we extend basically what you have covered in the past, and I'll just explain in what ways. And then next lecture, hopefully, we will talk about regression with qualitative variables. When you have some of your regressors, some of your x's, the x variables on the right-hand side, are providing qualitative information like yes or no, or like gender, male and female, or whatever. So this is something we'll talk about next lecture, okay? And then I'll talk about multicollinearity, heteroscedasticity. We make assumptions about the error term. and how it behaves. So, and since we will not know the error term, you don't see the error term. Has anyone seen the error term before? No, it's something you just make assumption about its behavior, how it behaves, and how you would like it to behave. Okay, so these assumptions need to be tested, and that's what we will be doing for the rest of the module. So when we talk about multicollinearity, heteroscedasticity, model specification or specification errors, all these have to do with the assumptions that we made about the error term and about how it behaves. At the end, which I call here diagnostic tests. So at the end, I will probably cover, give some introduction to how to do empirical research. So yeah, so that's what I'm planning to cover for the rest of the lectures. I know you using Eviews, so I thought you might be interested to know that you can actually have Eviews. I don't know if Jenkly told you already or not, but I thought it might be useful just to mention that. You could have a student version which expire in 6 months. I don't want you to have that one. Okay. You could have student version Lite for free on your laptop, so you can practice at home. All the data set I use in the lecture are on Blackboard. So that means you can reproduce the same results. You can practice at home how to do that. Okay. So, and I do encourage that. Okay, so you don't have to go to the computer lab to do so. You still can go to the computer lab if you want to, that's fine. But I'm just saying you should have Eviews on your laptop. And there's a video here, if you click, and that's, by the way, from time to time you will see these buttons on my slides. So that means this is a link to some external video or external resource, so something I'm asking you to follow. So for example, this is a short video, 4 or 5 minutes video to show you how to download Eviews Lite for free from Eviews website. And I'm sure I might have talking about the differences between different versions. So please download Eviews and try to practice, try to reproduce what the examples we cover in the lecture. So that's about Eviews. Of course, I know Godwin is delivering the practical sessions, but you still can have so much you can learn about Eviews. You can find so much online. On Hanomics, for example, there are a few videos I recorded for a different course. They are there, so you still can watch them. But I have to warn you, what I was trying to do here, I know you probably in your computer labs using the menus to implement different commands. But in this course, I was actually showing them how to write a script or a code to implement to do the same task, which is something I do encourage everyone to do. If you're using Eviews or any software, the idea is to be able to have a code that's written or a script of the steps you've done. So if you have, for any reason, if you have to do it again, so you don't have to repeat the same steps again and again, over again and again. So you have already the script, you've written it once, and it is done. So if you want to change anything, if you want to add anything, if you want to edit it, change a line in your code, then you actually have a record of what you've done in the past. So then all what you need to do is just to go back to that text or that script and then just change that script. And then click run, it will do all the steps again for you. So you don't have to do it yourself as well again. I'll show you, for example, how to export results or tables or graphs from Eviews. So you don't have to do screenshots. I hate screenshots. I don't like them. But so there are ways to do that in Eviews. But anyway, so this is what you can see on Hanomics. A few tutorials. Hopefully you will find them interesting. Also, there's a link here to a full set of tutorials. So whatever you want to learn is there. All the basics, everything you need to know about Eviews, how to use it, different data sets, different examples. Just follow that link on Eviews website. So again, whenever you see that button, that means it's a link. Click here, so it will take you directly to where I want to go. Okay, so as I said in the beginning, I'll start with a very brief recap to what we want to do when we have a regression model. why do we do regression, and then I will show you how this is relevant to the topic we will cover today. So when you do regression, you have a research question. You want to explain a variable, we call it y, or the dependent variable. And according to theory, we know that this variable depends on one or more variables. So these we call independent variables, or x's. So you have y depend on x. And because you cannot include all the variables, all the factors that affect y, then you have some error term. And the error term is one of the most important things in econometrics, because, as I said, you don't see it, you don't know it, you just make assumptions about how you would like it to behave. Okay? And then you test those assumptions to make sure you have a good model. Because this is, at the end of the day, this is an error. So you don't want that error to be very, you want it in average to equal 0. Okay? To be very, very small to equal 0, because that means you have a good model that explains the behavior of y, or your dependent variable. Okay? So in that sense, my task as an economics student or as an econometrician is to come up with estimations of these betas, so to know or calculate somehow how much these betas are, which will explain the relationship between x and y, between the independent variable and the dependent variable. And we know that the magic way to do that, the most basic way to do that, and the very magical tool to do that is the OLS. I will explain what that means now. So we call this equation a population or true model, these betas. So this is the true relationship between x and y. And when I talk about population here, I talk about well-defined entity that could be people, individuals, could be firms, could be cities, states, countries, anything that is well-defined. So for example, if I want to study the effect of, let's say, tuition fees or increasing tuition fees, changing tuition fees on enrollment at universities. So my population will be all students, or all those who are eligible to join university in the UK. So that's my population, okay? But we don't usually study the population because it's very costly to collect data about everyone in the UK, okay? So what we do instead, we actually look into a sample. And hopefully that sample, if that sample is, I mean, there are some conditions how you can have a random sample and sample that can represent the whole population. So any conclusion we'll make based on this sample, we should extend that to the population as well. So my objective here, as I said, is to explain that y, or the dependent variable, on average. Okay? There'll be some people, for example, if you want to have an equation that explains consumption, or food expenditures, for example. So let's say food expenditures depend on income, how much you earn. So how much you spend on food might depend on how much you earn in the first place, how much money you have in your pocket every month. Okay? So what I'm studying here is actually on average, if income changed by 1 unit, let's say £1, how that is going to affect the spending on food, okay? On average. Why on average? Because there'll be all people who spend more or less, but we are interested on the mean value of y, so the average change in y, okay? So on average, y will change by how much? By how much? But the value of beta, that's what we estimated. That's what we use OLS to estimate. So I have to emphasize, I always say this. What I started with is that theory should tell us or should inform your model. Meaning, if you really want to refer to a causal relationship, so X causes Y, this regression doesn't give you that. Okay? So what you see, this equation will not tell you that. So in your, sorry. So in Eviews, Eviews is not going to tell you whether food expenditure should be the dependent variable or should be the independent variable. Eviews doesn't understand. The software will not recognize that, so whatever you put there, it will give you results. So what we're trying to do here, we say, okay, the causality is going from X to Y, because according to economic theory, we understand that income is one of the important factors that determine food expenditure or consumption, okay? So that was based on theory. So again, just to make it clear, any causality has to come from, where does it come from? Hello? You still here? Okay, don't worry about taking notes. Just listen to me. So what I'm trying to say here, causality must be based on theory, not regression. Regression doesn't inform you or doesn't tell you anything about causality, because as I said, anything you put in Eviews will give you results. So, for example, if we know your consumption increases if your income increases, so that's what the consumption function look like, or that's what economics tell us about consumption function. So consumption depends on income, okay? So in Eviews, if you put income as a dependent variable by mistake, and consumption as independent variable by mistake, do you think Eviews will recognize that? It will not recognize that, okay? It will give you results, the output, and you might just go and explain something that is totally wrong, because causality should go the other way around. So causality from income to so income, changes in income causes changes in consumption, and that is not from regression, that's from economic theory. So causality must be based on economic theory. And given that you have in your model, when I talk about model, I mean equation. And what you study in this module is we call a single equation model. So you have only one equation with one dependent variable and a number of independent variables. So in any model, causality should be based on theory, not the model itself, not regression, not the data. It comes from economic theory. Okay, so the interpretation. So how do we interpret these betas? Okay, so a unit change, well, if you measure income by units, by pounds, and consumption by pounds, that means a unit change in income will cause or lead to a beta units change in consumption. Yes, thank you. Okay, so that's what we call the slope coefficient. We also have the intercept, which is beta naught. So how do we interpret beta naught? So what does it mean, beta? That beta 0. Can anyone tell me? Yeah, I can hear something, but I need it to be more louder so I can hear it here, so you're far away. So what is beta 0 here? What's beta naught? Is the intercept. Okay, so if you have a consumption function, consumption equal beta 0 plus beta 1, income plus an error term. So what does beta 0 tell? How do you interpret beta 0 here, beta naught? In this example, in the consumption function. Exactly. So this is the consumption level on average when your income equals 0. Okay, so that's the minimum level of consumption. But in general, beta 0 is the intercept. Okay, so this is the, and that's how you can explain it. And when we explain beta 1, the slope coefficient, we assume that other factors or other independent variables haven't changed, or what we call in economics always ceteris paribus. So nothing else changed. Okay, so as I said, we have the population. We can't study the population. We withdraw a sample from the population and we collect data from this sample about X and Y, and we use our magic tool here, which is the OLS, okay, the ordinary least square. What the ordinary least square does, it actually minimizes the error sum of squares, as you can see, and you should by now be able to derive actually equations or formula for beta 1 and beta naught, okay? So what you need to do is to take derivative with respect to the regression coefficient and make it equal 0, and that will give you beta hat, so the estimation or the OLS estimator. Okay, so we said, okay, we have an error term. We don't know much about that error term, but we make assumptions about how it behaves. Okay, and these assumptions about our model, the classical linear regression model, from 1 to 7, and these are the assumptions that we will be testing, not today, from next time. We'll be talking about diagnostic tests and how that is related to these assumptions. But the first assumptions we make about OLS, that the model is linear in parameters, and that is the rest of the lecture today. That's what we're going to talk about today. So our first assumption, we assume that, okay, the model is linear in parameters. Okay, we'll explain what that means. Okay, and different functional form in which actually the linear is still linear, the model is still linear in parameters. So we also assume that the regressors, the x's, are fixed or nanostochastic. The expected value of the error term should equal 0. Why? It's an error. Okay, so when that error on average to be 0, so you will see some points above the regression line, some points below the regression line. When you add these, they cancel each other. So on average, this should be 0. Okay, so that's what we call the expected value of UI given x equal 0. Assumption 4, we assume homoscedastic errors or constant, or errors with constant variance. So the variance is the spread of your data around the mean. So that should be constant, and we call it sigma square. I think next time we'll talk about what if this is not the case. How should we test for that first to know whether it is whether this assumption is valid or not, and then what to do if it is not valid. Okay. So and the next assumption, A5, no autocorrelation. There will be another lecture for that, and that means that the covariance between UI and UJ, so two errors, it should be 0. So that means they shouldn't be correlated. So there should be no correlation between the errors. No multicollinearity, so there's no relationship, linear relationship between the x's. So your independent variables are not correlated. And again, this will be another lecture. So again, these are we will spend the rest of the semester just talking about these assumptions, okay? So it's a good idea to know them now. Assumption 7, we assume that the model is correctly specified, and that includes the functional form, by the way, which we will talk about today. But then maybe in another lecture we'll talk about how to test for that. But today we'll explain what we mean by the functional forms, different functional forms, and how to interpret betas or the slope coefficients in each case. Okay? So no specification bias. That means in addition to functional forms, other stuff like you shouldn't omit or drop or ignore important variables. Do you remember we said when we study the behavior of the dependent variable, we need to include the important variables that affect y. We need to include these variables on the right-hand side. So what if there was an important variable that we are, for one reason or another, we ignored it, maybe we cannot measure it, or we didn't know about. So the effect of that variable goes to, where does it go? Where does it go? So there's an important variable that affects y we didn't include in the model. So it's not there. So it's not mentioned explicitly in your model. So it's not one of the x's in your model. So its effect will go into the error term, okay? It will go into the error term, and that is what we call omitted variable bias. We'll explain this later, so don't worry about it if you don't know what that is. Okay? So this is just another example of specification errors that we will cover in this module. But anyway, so as I said, this is just a broad overview of what I'm planning to do over the next few lectures, including this lecture. Okay? And as I said, in this lecture, I'll be talking about two things. Things that are related, the function form, which are related to two assumptions here. The first one, that the module is linear parameters, and the specification errors that are related to functional forms. Okay? So, hopefully now you know where we are and where we are going. Okay? Okay. So, if you have any question, don't wait till the end. Please ask me. You just raise your hand and say your question. So, if these assumptions, these are desirable assumptions, these are desirable properties of our error term, we want that model to meet all these assumptions, or these assumptions to be valid. And in that case, if that happened, and we were lucky for that to happen, because it's not usually the case, okay, and that's why we test for heteroscedasticity, we test for multilinearity, we test for autocorrelation. We want to have a good model, okay? So because in reality it's different. This is not the case. So one or more of these assumptions will not be true, and you have to deal with it. You have to correct this somehow, okay? So if we're lucky to say all these assumptions are true, then our lovely OLS produce a nice estimator that has desirable properties that we short it as blue. What does blue mean? So we have the best, linear, unbiased estimator. Perfect. Okay? So if these assumptions are valid, and we are lucky to have them valid, because as I said, in reality, it's not going to be the case. So then OLS estimator is blue, best, linear. You see, linear. Is that right? That's what we talk about today, because OLS deals only with models that are linear in parameters, and that's what we will talk about today. So what do you mean by unbiased estimator? Can anyone tell me? What do you mean by unbiased estimator? I'm not asking you to prove it. You might have done that already with Jenkly, but I'm not asking you to prove it now. I'm asking you to tell me what it means. Does anyone remember what that means? Okay. Let's just tell the story. very quickly. So you have a population. You can't study the population. What do you do? Can anyone tell me? Yes, you withdraw a sample. So you study the sample. You collect data for this sample, okay? And you use your magic with all this to get values for these betas. Is that right? Okay, so that was one sample, okay? What if I withdraw another sample and again use that magic all this to produce betas or to estimate betas? Am I going to produce the same values? No, it will be different. So I did this again and again, and every time I get slightly different value for betas, okay? But on average, so if I take the average of these betas, they should equal the true parameter from the population, which is the true beta, okay? So in other words, what unbiased estimator means that the expected value of your estimator of beta hat equal beta, okay? So unbiased estimator means the expected value of beta hat equal beta, okay? So I hope you will remember it from this story. So you have a population, you withdraw a sample, you calculate beta using a list, produce one number, you do it again, you get another number, but then you do this hundreds of times, but then you get average of all these estimation. That should be equal to beta. So if it is more than or less than beta, that means your estimator is biased, okay? And that's a problem. We don't want it to be biased. We want it to be cute and nice, unbiased, okay? So that's the first one. How about BEST? What does B stand for? Best estimator. So what do we mean by best? So if you have two or more estimators to choose from, so let's say we have our magical way, or less, but we want to compare the estimation from or less with another type of estimation. So the best one would have the minimum variance, okay? And that means your estimator is efficient or the best one, okay? So these are things or concepts that you really need to understand. So you don't just learn OLS is blue. What does that mean? It's best linear unbiased estimator. Again, what does it mean? Okay? So linear, we'll talk about today. Linear and parameters. I will explain that today. So the whole lecture is talking about that today and how to interpret betas in different functional forms. Unbiased means the expected value of beta hat of your estimator equal the true parameter beta. The best means it has the minimum variance. So if you have to choose between unbiased estimators, so if you have 3 or 4 estimators, different estimators, they're all unbiased, okay, so they meet the first one here, the unbiasedness, but then the best one will be the one that has the minimum variance. So you look at the variance, and the one that has minimum variance, that will be your friend. That will be your favorite one. Okay? So that's what I mean by blue. Anyway, so what do you mean by linearity? Okay, so as I said, I'll be talking today about this assumption 1, and that is also related to assumption 7. Okay? So the first assumption we made, that the model is linear in parameters. Okay? So what do you mean by linearity in this case? So if you look at these two equations, well, an equation is linear if the variables, in linear in variables, if you plot that function and it gives you a straight line. So that means it's in the very simplest form. So it's not raised to, the variables are not raised to any powers. Okay? Apart from 1, so don't write it. So the first equation is linear in variables. The second equation is not linear in variable. This is a quadratic function. So the first one is a linear function. The second one is a quadratic function. It has x squared. Okay? But both, okay? So they are not linear in variables, but look at betas. Look at their parameters. Okay? So they are linear in variables. Sorry, one of them is linear in variable. The first one is linear in variable, but the second one is not. But both are linear in parameters. Look, when you look at beta, beta is not raised to any power, it's not divided by anything, it's just beta. Okay? So it's linear in parameters. So if you want to see the difference, look at the first equation. So as I said, linear here means not raised to any power, not multiplied or divided by other coefficients, and etc. So the first equation is linear in coefficients. Now I'm looking at betas. The second one, although it is not linear in variables, because we have a quadratic function here, we have x squared. However, it is linear in parameter, because look at beta. Okay, it's alone there, so if it is lonely there, so that means it's linear in parameter. Okay, look at the third one. Is it linear in parameter? No, it's not linear in parameter. Okay, so what we are concerned about with all this is the parameters, is betas. As long as it's linear in betas, then we can use all this. So all this is our friend and will save us. We can use all this if it is linear. So this is one of the assumptions we made. Remember, assumption 1, the model is linear in parameters, not in variables, in parameters. So as long as betas are linear, that is absolutely fine. So which means that this equation can be estimated by all this. Well, the first equation is a quadratic equation. There's x squared, so it's not linear in variable, but still we can use all this. Okay, is that clear? The second equation, we cannot. So the second equation cannot be estimated by ordinary least squares, and you could, because it's nonlinear parameter, but it could be estimated by nonlinear least squares. And this is something you will not cover in this module, so you don't have to worry about. But you should understand that when you use OLS, you make the assumption that the model is linear in parameters. So you parameters enter the model in the linear form. Okay? Is that clear? Okay, great. Because that will take us to different functional forms now and how to interpret betas in each case. So far, we assume that the model is actually linear in variables as well. So we didn't talk about cases where the x and y are expressed in different forms. So I guess the examples you've covered so far tell you, okay, there's y equal beta 1, beta 1, x1 plus beta 2, x2 plus an error term. So you didn't look at what if y was in log form. What if both variables x and y were in log form? What if x only was in log form? How can I interpret beta in that case? So let's just look at how do we interpret beta if we have this linear form in the variables. So that's fine. I think now you're familiar with that. So 1 unit change in x will lead to beta units change in y. So if the example we're looking at is consumption function, so you have consumption as the independent variable or the dependent variable? Consumption function, where you would have consumption as dependent or independent? Dependent. That's what you want to explain. Okay, so that's your dependent variable. That's your y. That's the variable on the left-hand side. Okay, and on the right-hand side, what should I include on the right-hand side? What determines your consumption according to economic theory? It's your income. That's one of the most important factors that determine consumption expenditures. Okay? So, in that case, let's say consumption is measured by pounds, consumption expenditures are measured by pounds, and income is measured by pounds per week or whatever. Okay? So to interpret that beta in front of income, the slope coefficient, so that means when income increases by 1, when income increases by 1 pound, because it's measured by pounds, so this is 1 unit, then consumption will increase by the value of beta 1 units, okay, which will be pounds as well, okay, because consumption is measured by pounds, okay? So this is the simplest form. So what if we have another form where y is in log form, so log y, and x is in log form, okay? In that case, the interpretation of beta will be slightly different, okay? It is very similar, it's just the way you explain it, because now we have this model called elasticity, because you actually not looking at unit change against beta unit change, you're actually looking at percentage change against percentage change, okay? Do you remember elasticity from first year, okay? So what's the price elasticity of demand? You look at the percent change in quantity demanded against the percent change in price. So you look at the percent change. You're not looking at the unit change, okay? So when you have log model, so again, let's explain what that means. Log model means you have log y and log x. So log in both sides. In that case, this is called, as I said, constant elasticity model or elasticity model, because you can now interpret beta as percent change against percent change. So in that example, okay, if income and consumption are expressed in terms of log model, so what beta associated with the income, slope coefficient of the income, how would we explain that? How would we interpret that? So it's 1% change in income. So I didn't say £1 change. So I didn't say when your income increased by £1. So no. When your income increased by 1%, then your consumption will increase by beta %. Okay? Is that clear? So that's the main idea. One of the very popular examples here in economics, okay, is the Cobb-Douglas production function. Have you heard about that? Okay. So in Cobb-Douglas production function, you have two inputs. So the output is Q, and that depends on L. So these are your inputs, labor and capital. Okay. I can transform this model using the log. So if you take log on both sides, this will produce that, and I add the error term because I know that there must be other factors that will affect output that are not related to labor and input. There must be other factors as well. So that's why in econometric model we should include, or we do actually include, the error term. Okay? So in that case, this is called log or double log model, okay, or in a constant elasticity model. So because, as I said, because both x and y are in log form, and in this case, by the way, since we are here, we talk about Cobb-Douglas production function. The values, or when you estimate beta 2 and beta 3, so if you sum these two, beta 2, which is the coefficient attached to labor, and beta 3 is the coefficient attached to capital. So if you actually add these two, and if they equal 1, that means we have constant return to scale. Okay? So let's see an example. Okay? So in this example, as I said, the data, you'll find the data I'm using here on Blackboard. So under the folder for this week, you'll see the data in Excel format, in Excel sheet. So you can produce the same tables or the same results you see here. And I do encourage you to do that, to play with the data. So what we have here, we have cross-section data. So what do we mean by cross-section data? Since we're saying cross-section data, there are different types of data. There's no break before you tell me. Well, it's your decision now. We're not going home today. Can anyone tell me what do I mean by cross-section data? And what are the other types of data then? You don't want to have a break, really, do you? You're enjoying the lecture. Well, that's good news for me, if you're enjoying the lecture. Or maybe you are just quiet because you want me to finish as soon as possible so you can leave. So you see, the interpretation can go either way. Come on, guys. What do you mean by cross-section data? So what's the difference between cross-section data and time series data? Or panel data? You don't need to look at your notes. You need to understand. Because if you understand it, you wouldn't really need to go back to your notes. Okay? So listen to me. Cross-section data, okay? So that means you measure your variables for different units at one point in time. Again, what that means? So let's say if I want to have cross-section data for GDP, for example. So I collect data for GDP, let's say in 2019, this year, for 100 countries. So I have a number of units, but there is no time here, you see? There's no change in time. It's only one point in time. So that's cross-section data, okay? So cross-section data, you look at this point in time, you look at different units. Different units here could be countries, as in this example, could be individuals. So if you look, if you collect data about consumption and income, consumption expenditures and income, I could collect this in the form of cross-sections, which means that I come in one point in time, and then I ask thousands of people, or hundreds of people, how much their incomes and how much they spend on consumption. And that, in that case, so there's no time, there's no change in time, it's just in that point in time. Okay? If you look at the other side, the time series, that means I will actually take one unit and actually collect the data over time. So you see that? So this cross-section, you're moving that way in one point in time. For time series data, you're actually moving over time for one unit. So you don't have many units, you have only one unit over time. So in the GDP example, I will collect data for one unit, let's say the UK, not just this year, over the last 20, 40 years. So that's time series data. Okay? Why do you really need to understand this? Because when we talk about diagnostic tests, I'll show you that some of these issues, actually, problems, I mean, this is one of the reasons, of course. There must be other reasons you need to understand the difference. But one of the reasons is some of these issues or assumptions are usually not valid with certain type of data. So, for example, heteroscedasticity or unequal variance. Okay, this is one of the assumptions that we made, that the variance is equal. The error term has equal variance. This is not usually the case with cross-section data. So if your study involves cross-section data, I tell my students, by default, just assume there's a problem. There's heteroscedasticity issue. Okay? You still need to test for it. You still need to check for it. But I'm just saying it's something you would likely to encounter more in cross-section data. Okay? While autocorrelation, remember, when we assume no autocorrelation, that the errors are not correlated, this is something more specific to time, so time series, compared to cross-section. So this is something more common in time series data. So if you don't have a basic understanding what that means, panel data, time series or cross-section, then it's very difficult for you to address the question, and it's also sometimes it might not help you to come up with a good model. But anyway, panel data, by the way, you have both dimension in your data. So you have data for GDP for 100 countries, not one in point in time, over, let's say, 20 years. That's a panel data because you have both dimensions in your data. Okay? So this is the kind of thing that you should learn and know, and you don't need to look at your look for it in your notes. So this is something you should actually understand. Okay, it's very straightforward. It doesn't need really any proof or anything. Okay, since you didn't answer the question, would you like to have a break, or should I decide on your behalf what to do? Okay, I'll be very tolerant this time. Okay, so do you like to have a break? I know the answer before you ask. Before I ask. Okay, let's have 10 minutes break. No, 8 minutes. Okay, 8 minutes break and come back. Thank you. Okay, guys, that's 8 minutes exactly. It's 8 minutes exactly. So just coming on time. Okay, so where's the mic? Yes, here. Okay, let's start again. Is this mic working or not? It's working, yeah? Okay, great. Okay, so what we were talking about here is an example of log model. Okay, and what we are interested in here is to interpret the slope coefficient. Okay, how to interpret the slope coefficient, beta, in this case. Okay, so the example we have, as I said, the data is already on Blackboard, and the lecture notes, by the way. So these notes are in Blackboard. Okay, so so we have cross-section data. Table 2.1 has cross-section data, so that means we have data about 51 states. So our units here, our cross-sections here are states, and in one point in time, and that is in 2005. Okay, so what do we have data about here? We have data about output, measured as value added in thousands of dollars. We have data about labor and capital. Okay, so I know you know how to do this, and I'm sure you know how to do this in Eviews. Just trying to remember what the software is. Yeah, so ls means OLS, and then you add the dependent variable, which in our case here it's log, so it's len output. C is constant, or your beta node, and then len labor, len capital. So this is double log or log model. You remember? Okay. So, and this is the output. So how do we interpret these labor, these coefficients now? These estimated coefficients. Anyone help me, please, to interpret these coefficients? So what does that 0.468 whatever, what does that mean? So these are beta hats, yeah? So these are the estimators. These are the estimations. Okay? Or the estimated coefficients. Beta hats. So how do we interpret beta in a log model? So forget about this example. How do we interpret beta in a log model? You don't remember? I just said that 5 minutes ago. Okay, so it's elasticity model, meaning that you have a percent change against a percent change. So what is the dependent variable here? Is output. What is the independent variable we want to explain the coefficient for? Let's say labor. So if you increase labor by 1%, so that's the idea. It's not 1 unit. Okay? So if you increase labor by 1%, then the output will change or will increase because the estimated coefficient is positive. Okay? So it's not negative here, so it's positive. So that means it will increase by, yes, percent as well. So the output will change by percent. So this is the percent change in output, okay, by this value of beta, okay? So the same thing with capital, okay? And by the way, when you look at R squared, this is too high for cross-sectional data, and then we'll talk about this in a different lecture. But the model seems to be, okay, the coefficient seems to be statistically significant. How did I do that? How did I know that? How did I know that? How do I know whether these coefficients are statistically significant or not? Yes? I looked at the p-value, that's right. So you could look at the t-statistic. Yeah, but the R-square is high, as I said in this regression. It's very close to 1, yes. But when I talk about the individual coefficients, okay? So R-square represents the whole model. So it talks about the whole model, not just individual coefficients. But my question is related to individual coefficient. You're right. If you talk about the whole model and how much it explains, it's very close to 100%. So that sounds like a really high R-square. But for me, what I was talking about now is labor here, or lane labor here. That coefficient, the estimated coefficient, is statistically significant. You could do this by looking at the t-statistic. So how do we get the t-statistic here? How do you calculate this t-statistic? You've done hypothesis testing last week, is that right? Okay. So can anyone, do you have a mobile phone or any calculator? Could you please use these coefficients, okay? Divide these coefficients by the standard error. Divide these numbers, which I'm highlighting here, by the one next to it, the standard error, and tell me what you get. Can anyone do it for us, please? So it's 0.468332 divided by 0.098926. How much is that? Okay, it's 4.734 blah blah blah. So what is that? Is the t-statistic. Okay? So you know how to calculate that t-statistic now, okay? So in that case, our null hypothesis is beta is 0. So that's why, so ideally would say, okay, so this is the coefficient minus beta divided by the standard error. Okay? But because our hypothesis, or what we're actually testing here, whether beta equals 0 or not, so that's exactly the same. So when you say 0.46 minus 0 is the same, divided by the standard error, that will give you the t-statistic. Okay? So one way to look at the t-statistic, okay, and we know now hopefully how to calculate it, how to make a decision now to reject or not reject that hypothesis. The null hypothesis here is beta equals 0. So if beta equals 0, that means x statistically does not affect y. Okay? So how do we make a decision based on that t-statistic? You need to go to the t table. That's right. And you compare t-statistic with the critical value from the t table. Okay? Then if your t-statistic is greater than the critical value, then you reject. Yes, thank you. You reject the null hypothesis. That means it's statistically significant. Okay? Another way to do the same, just look at the p-value. Okay? So the p-value is very small. We compare p-value with the significance level. Okay? Usually it's 5%, 10%, or 1%. So in our case, we have nearly like 0 value for p-value. So it's very small. It's even smaller than 1%. So that means this coefficient is statistically significant at 1% level. Okay? Significance level. Okay? So you could do this two ways now. So you look at p-value, or you could look at the t-statistic, but then you need to compare with the critical value from the t-table. Okay? But sometimes, when you have a very small standard error, that produces a very large t-statistic, sorry. Okay? Then you don't really need to go to the table because it's very high anyway. So it's very large. It's 9 point something, 9 point, or 4 point. These are greater than 2. Do you know that the rule of thumb? Okay, so it's usually, it is large, so it's statistically significant. But in this case, anyway, we know it is statistically significant because we looked at the p-value and also looking at the t-statistic. It's very large. It's relatively large, so we can comfortably we can say, actually, yes, we reject the null hypothesis, and these coefficients are statistically significant. Okay, so these are the interpretation. This is the interpretation which you already said now. If labor increases by 1%, you see, I'm not saying by 1 worker or by 1 hour, okay? 1%, so percent change. Then output increases by 0.47%. How did I know that? Just go back to this estimated coefficient here. It's 0.46. You can round it up 0.468, so to 0.47, okay? So, and that's the percent change in output. If you actually add these up together, because this is a production function, so if you actually add up beta 2 and beta 3, and they're very close to 1, so as I said, this is in this case, it's a constant return to scale production function. Okay, so that's one case. So we have log or double log model. So log y and log x. So how to interpret beta? That's what we are concerned about. So that's what we want to know. Okay? So percent change against percent change. So how about if we have log in one side? So it's called log-lin model. Okay? Log-lin model. In that case, this is called semi-elasticity. So it's not elasticity model. The other one was called constant elasticity, but in this case, semi-elasticity. And sometimes, especially in modeling wage, so if you wanted to know the important determinants of wage, usually we use log-lin model, or at least we take the log of wage. And again, that because usually the distribution of wage is more skewed, so to make it closer to a normal distribution, so it's easier, it's helpful actually to take the log of the dependent variable, which is wage in this case. What is important to us is how to interpret beta, how to explain what that beta means, okay? So in that case, okay, so 1 unit increase in x, I'm not saying 1% change, you remember? So with the elasticity, with the double log model, I say 1% change in x. In this case, I'm not saying that because x doesn't have log. So it's 1 unit change in x. Okay? So 1 unit change in x. Okay? That will lead to multiply beta, or the estimated beta, by 100. Percent change in y. Okay? Is that clear? So do you see the difference? When you have a log-log model, you say 1% change in x will lead to beta percent change in y. So it's percent change against percent change. But in this case, we have a log-lin model. So log is only in one side with the dependent variable. Okay? So in that case, a 1 unit change in x, okay, will lead to 100 times you multiply beta 2 by the estimated beta 2 by 100, and that would be the percent change in y. Sometimes this is called the growth rate, because for small changes, for very small changes in x, this can be interpreted as a growth rate. And I'll show you what that means. Just an example. If I have log GDP, okay, so the dependent variable is in the log form, and on the other side, I have beta 1 plus beta 2 t plus an error, and t here represent the time. So if you have GDP, let's say values for 50 years, so t will equal 1, 2, 3, 4, so these like the time periods. So in that case, as we said, okay, if you multiply this by, so to interpret that beta 2, again, this be the growth rate of that real GDP. So in that case, let's see an example to try to explain what that means. So let's see, for example, we have data for real GDP in the US between 1960 to 2007, and this data in Blackboard. So I do encourage you to just play with the data and use it in Eviews. So in this model, we have LS, OLS estimator, Lin GDP, real GDP. So look in the left-hand side with GDP, constant, and then on the other and on the right-hand side, time. So it's not a log; it's just in units. So, and this is what we have. So, what does that mean? Can anyone explain that to me? What is estimated coefficient? Okay, for time. What does this coefficient mean? This is the estimated beta. What does it mean in this context? It's the growth rate of real GDP. Remember, this is the other side was time, okay? But let's explain it the usual way. Don't worry about what that means. Or yes. Yes. So exactly. So this is actually, so that means, okay, when let's say X changed by 1 unit means that every year. So this is the annual growth, okay? Growth rate. So in that case, you multiply that beta by 100, as you said. So how much would that be? 3.1. So 3.1%. That means that was the growth rate of GDP in the US between 2000. I don't remember the data. 1960 to 2007. So that was the annual growth rate. Okay. According to this example, it was 3.1%. Okay, so again, 1 unit increase in T or in X, sorry, will lead to 100 times beta 2 hat, of course, because these are the estimation, percent change in the dependent variable, which in our case here is real GDP. Okay, so this is one case. We already said that. Okay, so how about if it was the other way around? Okay, so we looked at log model, log-lin model. Now, let's look at the linear log model. Okay, so the log here in this case is on the right-hand side with the variable on the right-hand side with x. So you can see the example. So y equal beta 1 plus beta 2 log x. So x here is in log form plus some error term. So as I said, what am I interested in here is that how I'm going to interpret that beta 2. Okay, in this case, okay, so beta 2, that means a change in x by how much? I'm not saying 1 unit, by 1%. Okay, so if x changed by 1%, y changed by beta over 100. Okay, so the estimated coefficient divided by 100, that will give you the unit change in y, because y doesn't have log. So y here will be units, in units. Okay, so when x changed by 1%, because log is attached to x, you remember? So when x changed by 1%, y will change by beta over 100 units. Okay, because y here is measured by units. It's not percent change. Okay, so yeah, this is an example. So an example of this here we have annual expenditure function, and the data for this example again on Blackboard 2.8 table. So what do we have data for here? We have data on food consumed at home and total household expenditure, both in dollars, for 869 households in 1995 in the US. Is this cross-sectional data or time series data or panel data? Yes, cross-section. Why? Because we have units in 1 point, so a number of units in 1 point in time. So this is cross-section data. Okay? So, so we want to regress share of food, the variable called SFDHL, on the log of total expenditure, so lin expense. So in that case, the share of food expenditure, our dependent variable, is measured in units, but our independent variable, our x variable, is measured in the log form. Okay? So when you estimate this, can anyone explain that coefficient, please? The estimated coefficient. Not you this time. Someone from this side. So what does that mean in this context? Or in general, if you want to, if you don't want to comment on the example. So what does it mean? So we have a model where we have y is measured in units, and and x is in the log form. How do we interpret that? Beta, the estimated coefficient here. Beta hat, to be more accurate. Yes, please. Yes. Yes, exactly. So you divide that by 100, which means like 7.7 or 7.8. And in that case, remember, the dependent variable is in units. So it's not going to be percent change. It's going to be by units. $7.7 in that case, because that, I think, is that yeah, I think it's measured in dollars. So it's just very simple like that. So the idea here is how you interpret. Oh, sorry, I said it wrong. So when you divide by 100, it would be actually 0.0, and you add 2 more zeros, and then 7.7. So I said 7.7. That's wrong. It's actually, again, when you divide this by 100, you know, I'm sure you will use your calculator to divide it. But to divide this by 100, then you actually it's 0.000 and then 777. So it's not 7.7. I'm sorry. But anyway, so you know the point. You know what I mean. Okay. So so now we got the idea now. Okay. We looked at log model, how to interpret beta. Log-lin model, how to interpret beta. Lin-log model, how to interpret beta. So with log, you percent change, again it percent change. Okay? And then log-lin, so you have 1% change will lead to beta times 100. Is that right? Or the other way, sorry. Because it's log-lin, so so y is log. Okay? So the log on the left-hand side. So that means 1 unit change in x will lead to beta times 100 change in percent change in y. Okay, so when we have lin log, again, so you have exactly, and that on the other side change with by units. That's fine. So now what if we have a model like this, inverse model like this, where we have y equal beta 1 plus beta 2, 1 over x plus u. Can we estimate this by or less? This is not a linear model, but still linear in parameters. That's what we care about. Is that right? Yeah, so that's what we worry about with or less. We don't worry about x, the variables. We don't worry about x. We actually worried about the parameters. Okay, we worried about betas. So we still can use or less, and the interpretation here, the slope coefficient. Okay, the slope of this function will be minus beta 2 times 1 over x squared. So that means it will depend on the value of x as well. Okay? So, and you see the negative or the negative sign before beta 2. So that means if beta is positive, that means the slope will be negative, because negative times positive will give you negative. If beta is negative, then the slope will be positive throughout. Okay? So just notice that, note that negative sign before beta 2. So this is an example using the same data we used in the previous example. I ran this regression, but rather than using the log expenditure, I'm actually dividing 1 over expenditure. Okay, so 1 over x. So again, you can interpret that in that way, but I'll show you how to do that. Yeah. So if total expenditure increases indefinitely, so the share of food in total expenditure will eventually settle down to 8%. So let's see, that is the first coefficient. Okay. So just if you round that, it would be 8%, which is the beta one. That's the intercept here. So it's 0.077. So you can round that to 0.88%. On the other side, when you look at the slope coefficient, so it is positive. You can see it's positive 1331.3, and that suggests that the rate of change in your dependent variable with respect to the independent variable will be negative throughout. Remember, it depends on the sign when you look at this. So if it is positive, like our case, so that means the slope will be negative throughout this function. So this table here summarize all what we said so far. So what we want to understand here or to interpret is the slope coefficient. So how to interpret the slope coefficient. So looking at beta, and then the last column is just how to get the elasticity from that. So what we've been explaining actually was explaining that column, the slope coefficient column. Okay, so these are the linear model, log ln, ln and ln log model. Okay, so the last case I will cover is the quadratic function. When we have a model like this, where we have y depends on beta 1 plus beta 2x plus beta 2x squared plus some error term. So in that case, beta 1, okay, does not measure change in y with respect to 2, or with respect to x, sorry. Okay, so every time, or so far, we've been looking at the change in y with respect to change in x. So in this case, but when we did this, we assumed that other variables are not changing. So other x's, if we have more than one x in the model, so we assume, you remember ceteris paribus? That's the whole what the whole thing about is, just you assume that other other variables are or haven't changed. So this will be the partial effect of, or that's the impact of change in x on y. Okay, but in our case, can we really change x and assume that x squared is not going to change? That doesn't make sense. Okay, because both are x. So this is just x and the other one is just squared. So x squared. So we can't change x and hold the x squared constant. So that's why beta 1 in that case doesn't really measure the change in y with respect to x. And in this quadratic function, your slope will be beta 1 plus 2 times beta 2 times x. So you see so that means the slope again depends on the value of x, and you could actually calculate the turning point. Do you know how the quadratic function looks like? When you draw it, when you plot the quadratic function, exactly. So it's either U shape or the other way. Yeah. So there's a turning point. So if it decrease and then increase, then there's like a bottom point here. This is what we call the turning point. If it is inverted U shape, so if it looks like that, then there's a point at the top. This is again the turning point. You could actually calculate that turning point at what level of x, or where at x this turning point will happen by just applying this. So minus beta hat These are your estimation. 1 divided by 2 times beta. I think that's 2, beta 2. Okay, so it's just a typo here, I think. So, why would we need the quadratic function? Why would we need to measure or to include x and x squared? So in some situations, you want to see the relationship between x and y. Is it changing at an increasing rate or decreasing rate? So some of the functions you look at, you will have something like this. This is increasing, okay, but also it could be increasing at increasing rate or decreasing rate. So it depends really on, to capture this, you need that squared term, so the x squared. And I'll explain what that means with the experience one. So this is one of the very popular examples in economics when you try to model wage. So you include on the right-hand side different variables that we think they determine wage, how much you earn per hour or per week. Okay. It could include education, you could include other variables. But let's say here we want to study the effect of experience on wage. Okay. But we want to know how that affects. Is it the same for the first year of experience, or is it the same when you have 10 years of experience? Would that change? Would the effect on wage would change? We'll see now. So we estimated this model. Okay. So wage is our dependent variable, and on the right-hand side we have experience and experience squared. So these are the estimated coefficients. Now I want to explain how to remember how to explain the slope. So how to calculate the slope here? So it's beta 1. Remember this, beta 1 plus 2 beta 2 times x. Okay. So I'll show you how to use that. So looking at that, okay. First, let me look at the sign of experience squared. What is the sign? Is it positive or negative with experience squared, the estimated coefficient for experience squared? In this case is C3, the third one. Okay? It's negative. Okay? So that means it's actually diminishing. It has diminishing effect on wage. Okay? So as your experience increases, it will have less effect on your wage. Okay? So let me show an example. So first year of experience, so let's say you have only, so you move from, you graduated next year, and then you join, or this year, and you join the labor market. You had a job. So you are 0 experience. The year after, that means you had 1 year of experience. So once you have from 0 to 1, you had 1 year of experience. How much that will affect wage, depending on this model, that would be 30 cents per hour. Okay, so how do you calculate that? Let's say, just to make it easy to understand, how do we calculate that? Look at the second one, moving from second year experience. So you in your first year, so this is beta 1 is the, going back to this formula, remember this is beta 1, okay? So plus, sorry, beta 2 here is minus 0.006. So this is your estimated coefficient for beta 2. Look at C3, okay? So what is the number there? It's minus 0.00613, okay? So what that means, I don't know if you will see the cursor of this. Sorry. Yeah, so looking at here, so can you see this? Okay, so this is 0.006, that's my beta 2, beta hat, the estimated coefficient. This is 0.298, this is my beta 1, okay? And this is the intercept, which is the beta 0. So what we're looking at here, what we're interested in are these two values here, 0.298, okay? and minus 0.006. Okay, so the first year of experience, okay, is this one. So that's a 30 cent. Okay, so it's 0.298, so you can actually, it's, if you round it, it's like about 30, 0.30. Okay, 0.3. So how about the second year? So when you increase your experience by 1 year, so you have one more, would it give me another 30 cent increase in my wage? No, it will give you less. How did I know that? Because this sign here, the sign of beta 2, which is the estimated coefficient here, is minus. So it's minus. That means you expect to give you less than 30. And if you actually calculate how much exactly is worth the second year of experience, so remember, what is this number? This is your beta 1, estimated coefficient, beta hat, beta 1, okay? And what is this number? This is beta 2. It's minus 0.006. That's why you see this minus here. And 2 this from the formula. So you have beta 1 plus 2 times beta 2. Beta 2 here is minus, so minus times 2. That means this is minus. And then times x. X here, we said x changed by 1 unit. So you move from, you have only 1 to 2. So you move from having 0, to 1, and then you move from 1 to 2. So that roughly will give you 28 cents, which is actually smaller than, it's less than 30 cents per hour. Okay? So that's what we expected, because we know from this, having this here, this estimated value for this beta 2 here, minus 0.006, that's exactly what, if it was positive, that means it will increase with increasing rate. So this one, it increases. So the effect of experience on wage increases, but by a decreasing rate, because this is negative. If that was positive, that means it will increase by increasing rate. But because it is negative, our estimation here is negative, so we understand that, okay, if the first year of experience give me 30 cents per hour, then the second year of experience will give me only 28 or 29 cents per hour. So similarly, you can actually do this for moving from 10 to 11. That will give us about 17 cents per hour. So you see, it's decreasing. So it is still increased, so increase your wage, but at a decreasing rate. Okay? So as you have more experience, it increases your wage, yes, but it increases you by less. The turning point, you remember I told you could actually calculate this turning point here by following this. So you can actually find out at which x value your function will experience that turning point. Okay? So in this case, when we plot this, we'll see. So where's the turning point here? Is this one. Okay, so it takes that inverted U shape because it's a quadratic function, remember? So it will take this shape or the U shape or the inverted U shape. In our case, we have this inverted U shape. So the turning point here is a maximum point, so it's the top. Okay, and as I said, we could actually use this to calculate it here. So I use this formula to calculate and exactly at 24.4. So when your experience come to that point, then the effect on wage will actually start declining, which is exactly here. So when you have 24.4 years of experience, then the effect after that point, the effect will go down, will decline. So your function will go down. Anyway, so that is the quadratic function example. And just to mention a few things about R squared, the coefficient of the determination, and then we'll conclude with this. But before we jump to that, let me just wrap up what we said so far. Remember, the main point in this lecture is to focus on the different functional forms, and the important thing is how to interpret betas, okay, in each case. So we looked at log-log, log-lin, and linear log, and then the inverse model, and now we look at the quadratic function. So when you have a model with a quadratic function x squared. the final remarks or the final comments about the goodness of fit, the coefficient of determination, as you said in earlier, it measures the overall the goodness of fit or how the estimated regression line fit the data, or you can say how good my model is. So we're looking at how much of the variation in your y is explained by the model. Okay, so and the value takes from 0 to the value of r squared, the coefficient of determination, from 0 to 1. Okay, so 0 means very poor model, it doesn't really represent the data at all. 1 means perfect fit, means that's really super model that so we're looking at the percentage of the total variation of the dependent variable, as I said, that are explained by the regressors. So when you have a value of 0, that means no fit. When you have the value of 1, that means it's perfect fit. So if we if the change in y we can measure by the total sum of squares, we call it TSS. So this is the total variation, and this can be split into two parts. Some part which is explained by the model, which is called the explained sum of squared, ESS, and the other part which is the residual sum of squares. So basically, this one is like how much your model, how much of the variation is explained by your model. When I say the model here, I mean the x's in your model. So how many variables you include in the model, how much they explain in the variation of y. Okay. So the residual sum of squares, so that means this is the part of the variation that is not explained by the model. Okay, it's explained by the error or things that are not included in your model, and the total variation obviously is the sum of both, which is the total sum of square. So what I want to say here is that r square is the ESS, so this is the explained sum of squares, divided by the total sum of squares, and that because this ESS, that TSS or the total sum square equal the sum of these two, explained and the residual parts, then you can actually have this formula where the r square equal 1 minus the residual sum of squares divided by the total sum of squares. So if you compare, you could use r square to see how much the estimated model or your model explained from the variation in y. So if your r square, let's say 60% or 60 or 0.6, if your r square is 0.6, that means your model explains 60% of the variation of your dependent variable. So how about the 40%? So these are not explained in the model. So these are explained by the errors. Okay. So, but if you add more x's, if you add more independent variables, r square will increase. Okay, regardless of the importance of these x's. So you might be adding independent variables that are not actually explaining anything and not important, but because the way r square is calculated, the value of r square is going to go up. That's why we use also adjusted r square, because adjusted r square imposes some penalty on adding additional x's. Okay, so in that case, this is the equation for adjusted r square, and as you can see here, n is the number of observation, k is the number of parameters minus 1, TSS divided by n minus 1, again this is the number of observation minus 1. So if your model really poor, sometimes adjusted r square might be very, very smaller than r square, and sometimes actually can be negative, which is unexpected. That means there's really, really poor quality model fit. But you can use this to choose between R square or adjusted R square to choose between different non-nested sets of independent variables, meaning models that does not have model that, let's say, if we have a model of wage that depends on experience, and let's say we had this already, but if we add education, would that improve the model? So we can look at R square. Okay, so if, let's say, the model that has only experience was 60%, so R square was 60%, or the adjusted R square was 60%. If I added education and that increased R square, let's say, to 70%, so that means actually it's improved the model, so that means education could be added to that model. But unfortunately, this cannot be the case with the dependent variable. So you could also do the same. If should I use the income on the right hand side or the log of income, so I can compare between the functional form using R square. So if I use income only to explain consumption, and that give me 70%, but if I use log income and that give me 80%, so that means probably the log form is better than, or is performing better than the level form. Okay, but I can't do the same with the dependent variable. So if I have log y or y, I cannot compare these two models using R square, because R square measure the variation in the dependent variable, and in our case, in this case, if I have y and log y, okay, or if I have wage and log wage, these two are not the same. They are different. Okay, so the change or the variation in wage is much different from the variation in log of wage. Okay, so in that case, I cannot use R square to choose between these two models. Okay, but maybe it might be helpful if that was on the right hand side. But in the left-hand side, it's not very, very helpful. Anyway, so I think that's all what I wanted to cover today. Just to tell you what we said today. Okay, we did a recap, regression model, the assumptions, OLS, and we tried to link the discussion we had today to those assumptions, and I want you also to remember those assumptions. We focus on the functional forms. We talk about the goodness of fit R square. The reading for this lecture is chapter 6 in the textbook, Waldridge textbook. Next lecture, we'll talk about regression with qualitative variables. Do you have any questions? Do you have any questions? Okay. Thank you. See you next week.